I will wait for 2 more minutes if anyone else is joining. Okay, I will start the class. Everyone is able to see the screen? Okay. I am Honar Gupta. I am a PhD scholar at IIT Kanpur. I will do the review of this big one of this fundamental of supersonic and hypersonic flow and discuss some problems. If anyone has any doubt, they can unmute their mic and speak.
Good evening, sir. Manoj Kumar from DRDL, Hyderabad, sir.
Okay.
Sir, I am not able to see your presentation screen, sir.
Everyone else is able to see? Hello?
Your presentation screen is not visible, sir.
Everyone else is able to see the screen?
Other people, I am able to see the screen, sir.
No. I am asking other people if they are able to see the
I
screen.
am able to see, sir. Your screen is visible.
Then I think the issue is on your side, Manoj.
Okay, I will join, sir. Again, I will cut and join.
Okay. So in the first week, sir mainly talked about the uh, basic concept of compressive flow, thermodynamics, and talked about what is a supersonic and hypersonic flow. So I will also review about that and explain some problem. If someone has doubt related to this or some other doubt also, they can ask. So first I will talk about the perfect gas. Perfect gas is a gas in which the intermolecular force are neglected. So generally this assumption is valid for gas when the pressure is low and temperature is high. So according to this is the PV equal to MRT. This is the perfect gas equation. And here P is the pressure of gas, V is the volume, M is the mass of gas, and R is the specific gas constant, T is the temperature. It is also equal to nRT. Here this R is R bar, and this R and R bar both are different. R is the uh, specific gas constant, and R bar is universal gas constant. And value of this R bar is always constant, which is 8314.3 joule per kg mole Kelvin. And we can find the R using the formula R equal to R bar by M, where M is the molecular mass. There are one other form of the equation also. If we divide this equation by capital B, then we'll get P equal to rho RT, where rho is the density. So previous year there was one question related to this in the assignment, which was there was question density of fixed mass of gas can change if there were 4 options if volume remain constant. So density is given by m upon v. So if mass is constant is given, and if volume is also constant, then density will also remain constant. Pressure changes and temperature remain constant. PV equal to mRT. So mass is constant and T is constant, and if pressure changes, then volume density, sorry. So P equal to rho RT. So if T is constant and pressure changes, then density will also change. And from rho equal to m by v, if volume is changing, then density will also change for the fixed mass. And if the temperature and pressure both remain constant, then density will also remain constant. So answer for this question is B and C. Anyone has any doubt till now?
Sir, one doubt I am having, sir. In the assignment, only one option will be correct or multiple option will be also correct, sir?
Multiple option can also be correct.
Okay, sir.
So you have to check. So you have to check each and every option.
Okay, sir.
So there are two view. One is microscopic view and other is macroscopic view. In microscopic view, we see each individual atoms and molecule. So from the microscopic view of the gas, the collection of particles are in the random motion, and the individual kinetic energy of each particle contribute to the overall energy of the gas. And if this particle is molecule, then this molecule can also have rotational energy about axis, and it can also have vibrational energy. So these rotational and vibrational energy also contribute to the energy of the gas. And if this temperature is also high, then the electron inside the atoms can also have motion, and it can also contribute to the electronic energy of the gas. So energy of particle can have many different type of energy, like translational energy, rotational energy, vibrational energy, and electronic energy. And system is in equilibrium will depend if particles are in the state of maximum randomness. Currently, we will mainly focus on macroscopic view. This microscopic view will be discussed later in the course. In the macroscopic view, the gas is viewed as a continuum. In continuum, we see a collection of particles or atoms, and this collection of particles is chosen such that its density remain constant. Density is constant for this collection of particles. Like if let's say in a chamber there are random particles, and if we have a small control volume, then we choose multiple control volume, then depending on the number of particles its density can change. But if we have chosen the size of control volume such that uh, if particles, this density of both this control volume will remain same, then that assumption is taken as continuum assumption. And in macroscopic view, we see equilibrium when there is no gradient in the macroscopic properties like uh, in its property like velocity, pressure, and temperature, and chemical concentration remain constant throughout the system. For the equilibrium system of gas, where intermolecular forces are important, and also for the equilibrium chemical reacting mixture, internal energy and enthalpy both are function of temperature and volume. And if gas is thermally perfect gas, then it will depends only on the temperature. And this in case of thermally equilibrium perfect gas, the gas will not be chemical reacting, and we will ignore the intermolecular forces. And for the thermally equilibrium gas, the Cv and Cp both will also be function of temperature only. And Cv and Cp are also function of temperature. So if this Cv and Cp are also constant, then the gas is called calorically perfect gas, where E equal to Cvt and H equal to Cpt. Here generally we assume that at T equal to 0, E equal to 0 and H equal to 0. Is there any doubt till now? If no, then we will discuss some law of thermodynamics. So first is the first law of thermodynamics. So according to the first law of thermodynamics, sum of the work done on the system and heat added on the system is equal to the change in internal energy of the system. It is represented by this equation del Q plus del W equal to dE. Here this S B, this internal energy is a state function, point function. That's why it is written as dE, and this heat and work are both path function. It changes according to what path was taken to add the heat or work done on the system. That's why these are the written as del. This first law of thermodynamics is written for the closed system. For a given differential change in internal energy, there are in general an infinite number of different processes or ways by which heat can be added and work done on the system. So as this is the path function, so there are infinite ways it can be done. So there are mainly three processes we will focus on. One is the adiabatic process. In adiabatic process, there is no heat addition or not heat is taken away from the system. So del Q will be 0. So our equation will become del W equal to dE. And the reversible process is one in which there is no dissipative dissipative phenomena. So these type of phenomena are due to the viscosity, thermal conductivity, and mass diffusion. There is loss of energy generally due to that. So it can be shown that the work done on the reversible process is del W equal to minus P dV. So for reversible process, del Q minus P dV equal to dE. And when process is both adiabatic and reversible, then it is called isentropic process. In this case, the entropy will remain constant. ds equal to 0. So minus pdv equal to dE. Second law of thermodynamics is based on entropy, and it gives the direction to the process. It says that the change in entropy during any incremental process is equal to actual heat added divided by the temperature, del Q by T, plus a contribution from the irreversible dissipative phenomena of the viscosity, thermal conductivity, and mass diffusion occurring within the system, ds irreversible. So the entropy is given by ds equal to del Q by T plus ds irreversible. As this entropy always increases due to the irreversible phenomena, so ds irreversible is always greater than or equal to 0. For isentropic flow, this ds irreversible will be 0. So our ds will be dq, sorry, reversible process, ds irreversible will be 0, and so ds will be equal to dq reversible by t, and this ds will also be always greater than or equal to 0. These are some important relation in thermodynamics. TdS equal to dE plus PdV. We have seen the first law, dq equal to dE plus PdV. This was for reversible system, and for reversible system, dq equal to, if we write it in the form of entropy, then dq equal to TdS. If we substitute it, it will become TdS equal to dE plus PdV. Similarly, H equal to E plus PV. So dH will be equal to dE plus P dV plus V dP. If we substitute dE from this equation here, then we will get this equation. And for finding this equation for entropy, we can use this equation, dF equal to dH upon T minus V by T dP. Here we can write for calorically perfect gas, this dH will be equal to dPCT, and this T and V also we can write in the term of pressure, then and after integrating we will get this equation. And this equation is for isentropic flow. For isentropic flow, S1 equal to S2. It means this will become 0. So if we write simplified this equation, then we will get this P2 by P1 equal to T2 by T1 to the power gamma upon gamma minus 1 equal to root 2 by rho 1 to the power gamma. We have seen this equation also, PV gamma equal to constant. This is that only. Is there any doubt till now? Or if anybody wanted to ask any other question also, they can ask related to the course. Okay, then we will discuss.
Sir, pardon me, sir.
What?
Sir, in internal energy of gas, gravitational potential energy will be also considered, or vibrational, rotational, translational, these three one will be considered, sir.
I think this question is in the assignment, so I will tell this question. You think about it. I will tell this question in the next class. I think next class this
Okay.
last date will be over. You think about it. I think it
Okay.
was told in the uh, lectures also, and today also I told what type of energy are there. So you can watch the lecture again or see the slides. You will find it. All the assignment questions are very simple. You can generally, if you have watched all the lecture, you will find the answer of that questions.
Okay, sir. Thank you, sir.
No, I will not tell the assignment question before they are submitted. After the assignment is submitted, then you can ask the assignment question to me.
Okay, sir. Yes, sir.
If there is some similar question or something else related to concept or something, you can ask.
Okay, sir. Thank you, sir.
Okay, then I will talk about the compressible flow. Uh, Simply, if you see the word also compressible, then you know that the flow in which fluid can be compressed, that flow is called the compressible flow. That means the density of the fluid is not uniform, it can change. So generally, if density changes less than 5%, then we consider the flow to be incompressible. But in reality, no flow is incompressible. So this compressible flow assumption is always valid. We defined the compressibility using one constant tau beta compressibility, which will tell the about the fractional change of specific volume of the fluid element due to the high applied pressure change. Inverse of this compressibility is also known as bulk modulus. So what is the definition? Fractional change of the specific volume of the fluid element due to high applied pressure change. So if you write simply also, fractional change will be dou v by v, and high applied pressure can be del P, and minus sign is here because when you apply pressure to some fluid, its volume will decrease. So delta V will be negative if delta P is positive. So to make it positive, there is one negative sign. So in term of derivative, it will come tau beta equal to 1 by minus 1 by V dou V by dou P. Here V is the specific volume. So this is equal to 1 by rho. If we substitute it here, then dou V by dou P will be equal to minus 1 by rho square dou rho by dou P. If you substitute it here, you will get this equation. And there is one more relation which I will tell after this only. So dou P by dou rho equal to A square. So it can be substituted here and you will get this equation also. So this A is the speed of sound here. So the speed at which the small pressure wave propagate through the compressible medium is called the speed of sound in that medium. Generally, when in the compressible flow, then when flow is compressed, this sound wave, pressure wave travels, due to which this density and pressure will change. So speed at which this wave travel is called the speed of sound, and it depends on the medium also. So it depends on the compressibility of the medium, and it is given by you can see this is A. It is given by under root dou P by dou rho isentropic. This derivative is done by at the isentropic condition. So if you know that P B gamma equal to constant, it can also be written as P upon rho gamma equal to constant. So by using this you can find the dou p by dou rho. It can be dou p by dou rho 1 upon rho gamma minus gamma upon rho gamma plus 1 p equal to 0. If you simplify this, dou p by dou rho equal to gamma p upon rho, and T by rho can be written as RT from the ideal gas equation. So this will become under root gamma RT. It will become under root gamma RT. This under root gamma RT is only for perfect gas. Now we will define one more non-dimensional number which is used in the compressible flow, which is the Mach number. It tells about the domination of inertial force over the elastic force. Elastic force of the fluid flow is responsible for the propagation of the pressure waves across the medium. We have seen that this speed of sound depends on the compressibility, which is nothing but reciprocal of the this bulk modulus. So M equal to under root inertia force upon elastic force. So inertia force is given by rho a u square, and elastic force is bulk modulus of elasticity into area. This area will cancel, and K is given by rho. You see here, K is 1 by tau beta, and tau beta is this, so it will become rho dou p by dou rho. Rho dou p by dou rho, rho will also cancel. It will become u square upon dou p by dou rho. Dou p by dou rho is given by a square, so it will become u by a. Mach number is given by u by a. Now we will see how the shock wave is formed. So when the part, if there is one obstacle in the supersonic flow, this is the formation of shock wave in supersonic flow. So if there is obstacle in the flow, then this particle will collide to the obstacle, and due to its presence, this pressure wave will travel everywhere. It will travel everywhere, but it is mainly important in the upstream direction, because in the upstream direction, due to this flow, all this pressure wave will coalesce and form a strong compression wave. This strong compression wave is called the shock wave, and here this wave is in the shape of bow, so this is called bow shock. And this, just in the front of this body, this bow shock is the strongest. So from that point to the body, the distance between these 2 points is called the shock standoff distance. Like this, the pressure wave is formed. So shock wave is nothing but a gasodynamics discontinuity in which there is sudden increase in thermodynamic property. So just after you cross this shock wave, there is sudden change in gasodynamics properties. Like pressure will suddenly increase, temperature will increase, and its density will increase. So these properties will suddenly change. Generally, the shock wave also has finite thickness, but it is very less compared to whole flow. So, and the change is very large in very thin distance. You can see it is 0.1 mm distance, 0.1 or 0.5 mm distance. The sudden change is happening in the flow. That's why it is treated like a discontinuity. So, like before, told the formation of shock wave. Here also two cases are shown. One is the expansion Mach wave, and other is the one shock wave. So, in expansion wave, this this pressure waves does not coalesce to each other and they diverge to each other. So, these are all Mach waves. And in the case of the shock wave, this compression wave all merge to each other at some point and make up one strong shock. So there are these two types of shocks. Is there any doubt till now? Okay, then I will talk about the flow path and aerofoil over a range of Mach number. Let's say this is the aerofoil, and if flow is near Mach number 1, then what will happen that locally at some point over the aerofoil, the Mach number will be greater than 1, and due to which the shock wave will there will be shock wave on the aerofoil, which will again make the flow subsonic. And due to this shock wave, there will be the strong interaction with the boundary layer, and there will be flow separation. There are chances of flow separation also. If Mach number is slightly greater than 1, then the shock wave will shift to leading edge, and other part of the shock wave will shift to the trailing edge. And there will be formation of shock wave at the trailing edge due to the body, leading edge due to the body, and there will be formation of shock wave at the trailing edge to make the flow uh, uh, to keep the flow continuity. And if the Mach number increases higher than this, then the strength of this shock will increase and it will come nearer to the body. So when the strength of the shock increases, then due to which the temperature also increases, which causes the high temperature phenomena like dissociation, chemical reaction, and ionization also sometimes, which is the characteristics of the hypersonic flow. So generally hypersonic flow is associated with the flow at high supersonic Mach number, which is generally taken at greater than 5, but this is not a hard and fast rule. And generally these flows occur at reusable space shuttle, atmospheric re-entry, or ballistic missile, which fly through the outer extent of the atmosphere at hypersonic speed, or at the rocket at the high altitude. So in compressible flow, there is generally interaction between kinetic energy and internal energy of the fluid particle. So when the interaction is very large, like see here, when interaction is large, then if this is very near, then what will happen is temperature will increase and it will cause the recombination, dissociation, and chemical reaction, and even ionization of the fluid molecule. If all these are happening, especially these dissociation, recombination, and chemical reaction, then the flow is said to be hypersonic flow. The separation of different flow regime can be given by one one number beta, which is the ratio of kinetic energy and internal energy, which can be simplified by gamma upon gamma minus 1 by 2 m square. So for a low Mach number, there will be only excitation of translation and rotational energy mode. So for Mach number greater than 1, so it will be generally supersonic flow. When vibrational mode started excited, then it started going to the hypersonic flow. At the more high number of beta is increasing here. At more high beta, there is dissociation, recombination and chemical reaction started happening. This is also hypersonic flow, and if beta is very high, then there will be also excitation of the electronic energy modes, which causes the ionization. So generally we also call it by one different name, hypervelocity flow. But this is also hypersonic flow only. Only one more energy mode is added. So last year there was one question related to it. The ratio between the beta, ratio of the kinetic energy and internal energy, for two flows occurring at m equal to 2 and m equal to 6 is given by. So beta is given by gamma minus 1 by 2 m square. Gamma minus 1 by 2 m square. So if gamma is constant, then ratio at 2 Mach number will be given by ratio of the square of Mach number. So one is Mach number is 6, another is 2. So it will be 9. So like I told before, there is some flow characteristics of the hypersonic flow. So in the hypersonic flow, the shock wave will form closer to the body. I told here also, when Mach number will increase, the shock wave will move closer to the body. So the shock standoff distance will be less for the hypersonic flow, and the flow between, let's say, this is some body, then flow between body and shock, this region is called shock layer. And for the hypersonic flow, as this shock layer is nearer to the body, this shock layer is very thin, so it is called thin shock layer. So this is one characteristics of the hypersonic flow. It has thin shock layer. So due to the shock, this large amount of kinetic energy is converted to the thermal energy. So this changes to internal energy of the gas, so due to which it is heated. Flow is very heated after that. So this is called the viscous dissipation. This is due to the viscous effect within the boundary layer. So due to the viscous dissipation, there is enormous heating. So density of the, if temperature increases, then density, flow density reduces, and consequently due to which the boundary layer will thicken. The boundary layer will thicken. So when boundary layer thickens, then the outer inviscid flow will also change. So due to the change in outer inviscid flow, there is growth of boundary layer again. So there is one interaction between this boundary layer and outer inviscid flow, which is also called the viscous interaction. This is also one property of the hypersonic flow. And at the high temperature, flow become chemical reacting. So it is also possible that there might be there will be dissociation of the molecule and it can recombine again. So there will be chemical reaction happening also, which will alter its thermodynamic characteristics. So the calorically perfect gas assumption which we have used before cannot be used here, and we have to use the chemical reacting gas. And before we have also taken CBF and CP as function of pressure or temperature, as function of temperature. But for chemical reacting gas, as mentioned before, CB and CP will be function of temperature and pressure. So if you see the Bosock, its strength is strongest in front of the body. It is nearly a normal shock. So we know that across the shock there is change in entropy, and the most entropy change will happen in front of the body, and outer side of this has the less change in entropy. And as the strength of shock increases, the entropy change also increases. So due to which there is will be one if there will be a strong entropy gradient along the nose region of this body. So it will generate one type of entropy layer, and it will be till the large distances of the body. So this entropy layer is also one properties of the hypersonic flow. Is there any doubt till now?
Sir, one doubt I am having, sir. Sir, this kinetic energy dissipation will be in the boundary layer, and due to compressibility also will be there, no, sir, across the shock. Both region will be there for the kinetic heating. I am correct, sir?
Due to the inside the boundary layer, due to this viscous effect within the boundary layer, the flow will slow down. So
yes, sir.
So kinetic energy will be lost two ways. One is across the shock, and
yes,
one is other is inside this boundary layer due to this viscous effect.
Yes, sir. Across the shock also can we say this is also viscous loss only, sir? Because
across the shock is not viscous dissipation, but this inside the boundary layer it is called the viscous dissipation.
yes, sir. But this because of the across the shock isentropic flow will be not there, sir.
It will not be isentropic flow, but it is not called this there. It will also be due to viscosity only, but only this part is called the viscous dissipation.
Okay, sir. Thank you.
But there will be enormous heating inside due to this also, mainly due to shock.
Yeah. Yes, sir.
Any more doubt, or now we will do some revision of the compressible flow. So first we will talk about the normal shock. So normal shock, like I told you, shock is just a discontinuity which changes, due to which there is sudden jump in the properties across it. So let's say this upstream condition of P1, T1, ρ1, U1, and Mach number is greater than 1, then across the shock this pressure, temperature, density and density will increase and velocity will decrease, and Mach number will become less than 1 across the normal shock. So there are some assumptions for this normal shock. The flow is steady, 1D flow, and flow is inviscid. This flow is inviscid only on both sides of this shock. Inside the shock, this flow is very highly viscous, but it is very thin, so generally we neglect it. And flow is adiabatic, so there is no addition or removal of the heat. We are not doing any external work, and gas is taken as calorically perfect gas. So for finding the governing equation for this, generally we take a control volume like this around the shock, and apply all the governing equation containing momentum and energy. After applying this equation, we find the simplified equation. Content will become rho1 E1 equal to rho2 U2. Momentum will become P1 plus rho1 E1 square equal to P2 plus rho2 U2 square. Energy equation will be H plus E square equal to constant. So here we have currently 1, 2, 3, 4. 4 unknown and 3 equations, so we need more equation. And enthalpy can be written as CPT for calorically perfect gas. This is due to the calorically perfect gas. And as for perfect gas, we can also use the equation of state, that is P equal to rho RT. Using these 5 equations, we can find the all unknown U2, P2, O2 and H2 also. So we can write all these equations in terms of Mach number also. So after writing this equation in terms of Mach number, we will get this equation m2 square equal to 1 plus gamma minus 1 by 2 m1 square upon gamma m1 square minus gamma minus 1 m square and gamma minus 1 by 2. We can also get m star square equal to gamma plus 1 m square upon 2 plus gamma minus 1 m square. This m square is nothing but m upon nothing but u upon a star, and a star is under root this a star is at the sonic critical value gamma r t square. And rho 2 by rho 1 equal to u2 by u1, and we will get gamma plus 1 m1 square upon 2 plus gamma minus 1 m1 square, and p2 by p1 equal to 1 plus 2 gamma upon gamma plus 1 m1 square minus 1. Similarly, there is one more relation for p2 by p1, and t2 by t1 we can find using the equation of state. So all these relation, how to derive that, you can read in the book also, Compressible Flow by Anderson or some other book which is comfortable for you. These you can find in any compressible flow book. So if we see the relation and plot it, we will get curve like this. So if we see that at Mach number m1 equal to 1, we will get m2 equal to 1, and if we increase the m1, m2 will reduce from m2 from 1, and it is generally going to some constant value. And if we make m1 less than 1, then we will get m2 greater than 1. But there is one issue. For normal shock to be there, m1 should also be greater than 1. It can be found from the entropy relation. If we, there is one entropy relation I told before. This relation F2 minus F1 equal to Cp log T2 by T1 minus R log P2 by P1. If we use this relation and found P2 by P1 and T2 by T1 values, then we will get the relation of S2 minus S1 upon R and Mach number. If we plot it, we will get this curve. And if you see this, then you will see that S2 minus S1 upon R is greater than 0 only if M1 is greater than 1. So from the second law of thermodynamics, this delta S should always be greater than or equal to 0. So M1 can never be less than 1. We will see one problem related to normal shock. A strong normal shock wave with pressure ratio of 29 across it is traveling into a stationary air at T equal to 280 Kelvin in a straight duct. The magnitude of the air velocity behind the shock wave is. So one shock wave is traveling in the stationary air, we have to find what will be the velocity behind it. We have seen only this stationary shock, but this problem is related to moving shock. So to solve this problem, what we do it, we take the reference such that the shock become constant, shock become stationary. So let's say the shock velocity is c, and this velocity is v. So if we make, let's say here, add minus c velocity everywhere. Let's add velocity c in opposite direction. So this will come at a stationary. This velocity we will get c, and this velocity will be c minus v. So now this is the same as a stationary shock problem, where our u1 equal to c and u2 equal to c minus v, and we know that pressure ratio is 29. So this is P2 and this is P1. So P2 by P1 is 29 and T1 is 280. 280. So now we have to find value of V. So to find it, first we will use this pressure ratio formula, which is P2 by P1 equal to 1 plus 2 gamma upon gamma plus 1 m1 square minus 1. Is there any doubt? No, then if we will put this P2 by P1 here, gamma value is given 1.4. We have to find m1 square minus 1. So if we use the calculator to find, it will be we will get m1 equal to 5. You can also solve it, you will get the same. Now we know m1 equal to 5, then we can get the u1 equal to m1 under root gamma r t1. T1 we know 280, and this u1 equal to c. u1 equal to c. So we will get it. M1 is 5 into it is 1677.08 meter per second. There are many ways to find it, so we can use this formula also directly. P2 by P1 equal to 1 plus gamma m1 square upon 1 plus gamma m2 square, and for finding V we need T2 and M2. First we will find the root 2 by rho 1. We know M1, so it will be gamma is 1.4 plus 1 into 5 square upon 1.4 minus 1, 5 square plus 2. It will be this rho 2 by rho 1 will be 5. And according to continuity, rho 2 by rho 1 equal to u1 by u2. So u1 by u2 equal to 5. So we will get u2 equal to u1 upon 5. u1 was 1677.08. So u2 will be 335.416 meter per second. We got u2 and u1, and we got u2 335.416 meter per second, and u1 1677.08 meter per second. So V will be equal to C minus u2, and C is nothing but u1 minus u2. So it will be 1341.66 meter per second. This is the answer. This is the one problem for the normal fork. You can practice problem from the book also. Is there any doubt? Now then we will see what is oblique fork. So oblique forks are also a fork. These are made when there is one compression corner. So compression corner is something like this, which is shown here. It is a concave corner, or it can be due to the symmetric base also. When the flow has to turn towards itself, here you can see this flow, it is turning towards itself only, then generally oblique forks are formed. So in oblique fork also there are some assumptions. This is the oblique fork. This flow upstream is V1 M1 and downstream is V2 M2, and due to this wedge, let's say this angle is theta. This angle is theta. Due to this theta angle, flow will also turn at theta angle. And it is V2 M2. And we have taken one control volume like this and resolve all the velocity in normal and tangential direction of the fork, due to which we got U1 Mn1, U2 Mn2, and W1 Mt1 and W2 Mt2. We have taken at this assumption. This is a 2D flow. Unlike the normal fork, it is 2D flow. We have taken assumption of steady flow, inviscid flow, adiabatic flow, and there is no external work, and there is no body force, and the gas is calorically perfect gas. For continuity, same as before, rho 1 u1 equal to rho 2 u2. In momentum, there is one more thing. This u1 and u2 are, and w1 w2 are component of this v1 and v2. So in momentum we will get the two equation. X momentum we will get p1 plus rho 1 u1 square equal to P2 plus rho 2 UT square, and in Y W1 equal to W2. Here you can think that this is X and this is Y. Y is along the sock and X is normal to the sock. Energy equation is same as before, H plus U square upon 2 equal to constant. Enthalpy is same for the calorically perfect gas, H equal to CPT. And equation of state is P equal to rho R T. On solving all this equation, we will get equation in term of Mach number. So as we have resolved Mach number, flow to the normal and tangential to the sock, we will get Mach number mn1 equal to m1 sine beta and mn2 equal to m2 sine beta minus theta. If you see this oblique sock along the perpendicular direction to the sock, it behaves same as normal sock. And in the tangential direction, there is no change in the flow. So mn1 is generally greater than 1 and mn2 is less than 1, same as the normal sock. But as sine beta minus theta is less than 1, mn2 can be greater than 1 or less than 1, both. So similar to normal sock, we also get rho 2 by rho 1, P2 by P1 and mn2 square. So if you see the equation carefully, it is the same as the normal sock, only m1 is substituted by mn1 and in both the equation. So using the first, we have to find the sock angle. We don't know the sock angle. Without the sock angle, we cannot find the mn1. So for finding the sock angle, there is one theta beta m relation. Theta beta m relation, which gives tan theta equal to 2 cot beta m1 square sin square beta minus 1 upon m1 square gamma plus cos 2 beta plus 2. Using this equation, we can find the beta, and using the angle beta, we can first find the mn1. Using mn1, we can find the other properties rho 2, p2 and t2 and m2. Similar to normal sock, also across the oblique sock, P2 is greater than P1, T2 is greater than T1, rho 2 is greater than rho 1, and P02 is less than P01. Only M2 here can be greater than 1 or less than 1, it depends. If we plot this theta beta m on a graph, we will get this plot. So if you put here, instead of beta, if you put 180 minus beta also, you will get one more solution. Sorry, not 180 minus beta. Here we can get the two solutions for beta. So if we plot this, we will get this curve. So here there is one theta max for a particular each Mach number. These are plotted for different Mach number. So at every different Mach number there is one theta max. So at theta max, what will happen that we will not get the solution for this oblique shock. If theta is greater than theta max, we will not get the uh, solution for the oblique shock, and this equation will not be valid, because what will happen that currently this oblique shock is attached oblique shock. If theta is greater than theta max, this oblique shock will be detached from this corner. So this solution will not be valid. And we get for one theta and m, we can get the two solutions. One is for weak shock and one is the strong shock. Generally only we will get the weak shock only. Strong shock is we get only for in some particular cases only. So more prominent is only the weak shock solution. We will solve one problem related to oblique shock. An oblique shock is inclined at an angle of 35 degrees to upstream flow of velocity 517.56 meter per second. Deflection of flow due to this shock is 5.75 degree and temperature downstream is 182.46 Kelvin. Assume the gas constant R equal to 287 joule per kg Kelvin, specific heat constant gamma equal to 1.4 and specific heat at constant pressure Cp equal to 1005 joule per kg Kelvin. Using conservation relations, Mach number of the upstream flow can be obtained as. There can be many different ways because we have given so much data, but we don't have to think so much. Here this shock angle beta is given as 35 degree and deflection angle theta is given as 5.75 degree, and we have to find m, Mach number. So we can directly use the theta beta m relation. So if you put theta and beta value in this, we will get tan 5.75 degree to cot 5.7 to cot 35 m1 square sin square 35 minus 1 upon m1 square 1.4 plus cos 2 into 35 plus 2. If we solve this, for solving this we have to use calculator. So 10 5.75 0.1007 to 21.428 m1 square and the sin square 35, directly I am writing 32899 minus 1 on m1 square 1.4 plus cos 70 will be 1.742 plus 2. Now we can simplify it and solve, and we'll get the value of m1. Now we will discuss about the Prandtl-Meyer flow. So we have seen what happens when flow is at the concave corner, and now we will see what happens when flow is at the convex corner. So when flow turns away from itself, this Prandtl-Meyer wave form. Generally, this Prandtl-Meyer wave is the combination of Mach waves. Here, like this individual lines are shown, these are the Mach waves, and the starting and ending of this Mach wave depends on the upstream and downstream Mach number and angle by which it is reflected. There are some assumptions for the Prandtl-Meyer flow. As these are Mach waves, the flow is isentropic flow. It is steady and 2D flow. There is no external work, and gas is calorically perfect gas. So this upstream Mach number, Mach angle is this mu1 is Mach angle. This Mach angle is given by this relation mu1 equal to sine inverse 1 by m1. Similarly, this mu2. This mu2 is given by sine inverse 1 by m2. So when we solve the governing equation for this Prandtl-Meyer flow, we get one Prandtl-Meyer function, which is given by mu. Mu m equal to under root gamma plus 1 upon gamma minus 1, tan inverse gamma minus 1 upon gamma plus 1, m square minus 1, minus tan inverse under root m square minus 1. Let's say this flow is turned by angle theta 2, then this theta 2 will be given by mu m2 minus nu m1. The starting of this Prandtl-Meyer wave is called forward Mach line, and the ending is called rearward Mach line. So first, using the Mach number m1, using the Mach number m1, we find the mu1, or Mach number m1, we find the nu m1. Then using the theta 2 and this relation, we find nu m2. Then using this relation for m2, we find the m2. And this equation can only solve numerically. And as flow is the isentropic flow, we can use the directly isentropic relation, which is given by T1 by T2 equal to 1 plus gamma minus 1 by 2 m2 square upon 1 minus gamma minus 1 by 2 m1 square, and rest of the relation for the isentropic flow. Some physical trends which we can see is that generally for the shock wave, we have seen that temperature, pressure, density increases, but here temperature, pressure and density decreases. Here this flow is isentropic, so T01 will remain constant, total temperature and total pressure will also remain constant, and Mach number increases here, and m1 should also be greater than 1 for the formation of Prandtl-Meyer wave. As I told before, for solving the problem, first find nu m1 from the Prandtl-Meyer function and obtain nu m2 using the theta 2 and nu m1. Then calculate m2 using the Prandtl-Meyer function for nu m2. And as the function is isentropic, we can use this relation to find isentropic relation to find the T2 and T2 and rotor also. So this is one problem for the Prandtl-Meyer wave. Is there any doubt till now? You can ask doubt related to whatever I told about till now, or whatever was in the class also, online lecture. Today, as there was only revision for the, you can say, compressible flow and thermodynamics. So there is, you might already know all these things, and for the further details in all these things, you can read from the book also. Okay, then I will talk about this problem. A trace from film photograph of the flow around the corner reveals the edges of the expansion fan as shown below. The leading and trailing edges of expansion fan make the angle as shown. This is the leading and this is trailing edge of the expansion fan. These are the angles which are given. Assuming gamma equal to 1.4, angle of expansion fan in degree is, we have to find this expansion fan angle. Generally it is denoted by phi. So if you see what will be the mu1, this will be the mu1. And what is this angle? This is angle theta 2. And this 20 is mu 2. So what is the mu1? Mu1 will be 180 minus 143 degree. It will be 37 degree. And you know mu2 is 20 degree. If you see from here, this diagram, phi plus mu2 equal to mu1 plus theta 2. Then if we found the theta 2, then we can get the phi. So first we have to find what is m1 and m2. We know that mu1 equal to sine inverse 1 by m1. Then m1 will be 1 upon sine mu1. So m1 will be 1 upon sine 37 degree. This will be 1.67. 6616. Similarly, m2 will be 1 upon sine mu2. Will be 1 upon sine 20 degree, which will be 1 upon, which will be 2.9238. Now we know the m1 and m2, then we know what will be the theta 2, nu m2 minus nu m1. So we can find nu m1 by putting value of m1 here. It is 1.4 plus 1 and 1.4 minus 1, tan inverse under root 1.4 minus 1 on 1.4 plus 1. m1 is 1.66 66 16 16 square minus 1 minus tan inverse under root 1.6616 square minus 1. Using the calculator, it will be 8.696. Similarly, V12 we will put the value of M2 in the Prandtl function. And we get 13.493. For theta 2 value U M2 minus mu M1. Which will be 4.797. So using this, phi equal to mu2 equal to mu1 plus theta 2. Let me check if I made any mistakes in here. One mistake I made. Bit. This value is 16.6505. I put the wrong value in the calculator. And this is also will come 48.2653. So this difference will come 31.6149. So now we see this relation 5 plus mu2 equal to mu1 plus theta 2. Mu2 was 20 mu 1 was 37 and theta 2 was 31.6149. So we will get phi equal to 48.6149. You can try different problem for this shock, all type of shock, normal shock, oblique shock, and Prandtl-Meyer wave. You can read the relations, different relations in the thermodynamics. You can do the revision of both thermodynamics and compressive flow. It will be very useful in the course. Now we will see the flow through the nozzle. Let's say this is CD nozzle, converting diverging nozzle. Before the feeding nozzle, this is the control surface, and these are the assumptions which will take steady flow, coffee bundy flow, because generally the flow we assume that there is very area change is very gradual, so there is very less change in the velocity in the bidirectional. And adiabatic flow, we assume there is no addition of heat or any release. In viscid flow, no external work and calorically perfect case. After applying the governing equation, we will get simplified form of the equation, which is rho1 u1 a1 equal to rho2 u2 a2. This station 1 we have taken at the inlet of the nozzle, and station 2 at the exit of the nozzle. At the 1, properties are denoted with subscript 1, and at 2 it is 2. Momentum equation is given by this. This term is due to the control surface, this control surface. This is the for the surface of the nozzle, S. And energy equation is same. Enthalpy will remain constant. Total enthalpy, and enthalpy is given by CPT for calorifically perfect gas, and equation state is P equal to rho RT. For variable area change, there is one relation which we can find, which is area velocity relation. It is given by dA upon A equal to m square minus 1 du upon u. If m tends to 0, it corresponds to the incompressible flow. If let's say m is less than 1, then what will happen is this dA upon A, this and this m square minus 1 will be negative, or m square minus m less than 1, this m square minus 1 will be negative. So what will happen if there is decrease in area? Let's say dA is increasing, then du will decrease. If area is increasing, then velocity will decrease, and if dA is decreasing, then du will increase. If area is decreasing, then velocity will increase. Like here, for Mach number less than 1, if area is decreasing, then velocity will increase. If area is decreasing, then velocity will decrease. Sorry, if area is increasing, then velocity will decrease. Similarly, for Mach number greater than 1, m square minus 1 will be greater than 1, 0. So dA upon A, if dA will increase, then du will increase. and if dA will decrease, then du will decrease from the acceleration only. So where area is increasing, so velocity is increasing. Where area is decreasing, so velocity is decreasing. Before, by mistake, I told this is CD nozzle, but this is only a simple nozzle also. So in CD nozzle, generally, it is combination of converging and diverging section. So this is the CD nozzle, this is converging part, and this is diverging part. So if upstream Mach number is less than 1, then what will happen, that first Mach number will go to m equal to 1, because this is area, the area is decreasing, so Mach number will increase, u will increase, and here area is increasing, so Mach number will increase because u will increase because here m is greater than 1 this side. Opposite is also true. If Mach number is greater than 1 here, then velocity will decrease and it will further decrease if in the divergence section. Now we'll see this condition depends on the back pressure also later. There is one area Mach number relation which is given by this: A by A star equal to 1 by m 2 upon gamma plus 1 1 plus gamma minus 1 by 2 m square to the power gamma plus 1 upon 2 gamma minus 1. Here A square is area at the sonic condition, m equal to 1. So we can see that for a single area ratio there are two solutions. One is supersonic and another one is subsonic. Only for area ratio 1, because it will become m equal to 1 only. So we get the two solutions, and this solution depends on the which solution will be prominent will depend on the back pressure in the nozzle. So from this also you can see that this is A by A star is always greater than 1. A by A star is less than 1, then it is not possible for A by A star to be less than 1 for the isentropic flow. This is found for the isentropic flow only. These points are the same which I mentioned before. Now we will see what does the changing the back pressure does to the flow through the feeding nozzle. First we will define the critical point. So what happens that through the nozzle is that when let's feeding nozzle, what happens here, if let's say here now this is stagnation condition, at stagnation b equal to 0, and this is p naught. Let's say here pressure is p naught and we started decreasing from that. What happened initially, this velocity will increase, then at the throat it will become maximum, then it start decreasing again, because for increasing velocity in the divergent section there should be at least Mach number 1 here, but at pressure is not that low, it will not reach that like shown here. So at one point what will happen, at the throat this Mach number will become 1, and flow will become choked. That point, that pressure at which the flow becomes choked first, it's called the first critical point, and this is the maximum mass flow rate through the throat. At that condition, Mach number at throat will become 1 and area of the throat will be equal to A star. And exit Mach number is still less than 1 because it is subsonic. We have seen that there are two solutions for the area ratio. One is subsonic, other is supersonic. Currently it is really subsonic because back pressure is not that low. And exit pressure will be equal to back pressure. Flow is fully isotropic and subsonic. If pressure is between this P naught and first critical point, it will also always remain subsonic. Now if we decrease the pressure further, then there will be one normal shock inside the divergent section, due to which what will happen that first pressure velocity will increase till the normal shock. After that velocity will flow will become subsonic and it will match the back pressure. And as we decrease the back pressure, this location of this normal shock will move toward the exit, and there will come a point when it will be exactly at the exit. That is called the second critical point. And at that point, Mach number at throat will be 1, area ratio, throat area will be equal to A star, and at the exit Mach number will be greater than 1 at one side, other side it will be subsonic. Similar to the pressure also, one side it will be related to the supersonic condition, and another side it will be related to it will be equal to back pressure. So P equal to back pressure. It will remain isentropic till the upstream of the shock. Now if we reduce pressure further more, then let's say at some point we will reach another critical point at which flow will become fully subsonic, and there will be no shock, or it will be correctly expanded also. At that point, Mach number at exit will be greater than 1 and exit pressure will be equal to back pressure. It is corresponding to the area ratio. Supersonic Mach number will be corresponding to the area ratio AE by A star. Now if pressure is between the second critical point and third critical point, then the first nozzle will be flow will be overexpanded. Flow will be overexpanded, and due to flow overexpanded, there will be oblique shock just after the nozzle, which will increase the pressure of the flow. So flow will remain isentropic till the exit. After that, there will be oblique shock, which will become non-isentropic, and due to which there will be oscillation of pressure also, because oblique shock will increase pressure more than the back pressure. Then there will be expansion wave which will reduce it. So there will be oblique shock and expansion wave form at the exit to bring the pressure P equal to PV. Now if we reduce pressure further than the third critical point, then flow will become under expanded. So due to the under expansion, at the exit there will be a first expansion wave, then oblique shock, because expansion wave will increase pressure more than or decrease pressure more than what was necessary to bring it to the back pressure. So there will be series of expansion wave and oblique shock at the exit, and pressure flow will become isentropic till the nozzle exit. Now we will see one problem. Related to CD nozzle. A D-level nozzle is to design for an exit Mach number of 1.5. The reservoir conditions are given at P0 equal to 1 atmosphere, gauge T0 equal to 20 degrees Celsius, gamma equal to 1.4. Assuming shock-free flow in the nozzle, the exit absolute pressure is. Here we have to find the exit absolute pressure. So let's say this is the CD nozzle. We are given P0 equal to 1 atmosphere, gauge. So in absolute it will be 2 atmosphere. T0 will be 20 degrees Celsius, which will become 293 Kelvin. And exit Mach number is 1.5. This is supersonic Mach number. So exit Mach number can be supersonic only when there is isotopic flow throughout the nozzle. We have seen before. So to be isotopic flow throughout the nozzle, we can apply isentropic flow formula. This P1 by P2 equal to 1 plus gamma minus 1 by 2 m2 square upon 1 minus gamma minus 1 by 2 m1 square gamma upon gamma minus 1. At m1 is 0 because flow is stagnation. So we have to find only m2. Check the formula. So P0 upon PE equal to 1 plus gamma minus 1 by 2 m E square gamma upon gamma minus 1. This is the formula, I think. Gamma upon gamma minus 1. P0 is 2. To find PE, gamma is 1.4, M is 1.5, 1.4 upon 0.4. We'll put this value in the calculator. Is 3.671. So PE will be 2 upon 3.671. It will be 0.545 atmosphere. This is the answer. So we have discussed the compressible flow, normal shock, oblique shock, container wave, flow through the nozzles. Discuss something about the thermodynamics also, first and second law of thermodynamics, and some relations, important relations. What is the shock wave? What is the hypersonic flow? And uh, what uh, the, what are the properties of the hypersonic flow? Now, this velocity potential equation that was also taught in the class. So I will tell all the equation. For the inviscid compressible flow, there is Euler equation which is given by dP equal to minus dV dV. Now vector velocity v can be given by u I cap plus v j cap plus w k cap. If flow is irrotational, then the curl of velocity is always 0. So curl is given by, velocity is given by this, dou w by dou y minus dou v by dou z I cap minus dou w by dou x minus dou u by dou z j cap plus dou v by dou x minus dou u by dou y k cap equal to 0. For it to be 0, these all three individual terms should be 0, which means dou w by dou y equal to dou v by dou z, dou w by dou x equal to dou u by dou z, and dou v by dou x equal to dou u by dou y. In the vector calculus, there is one property that curl of gradient of any scalar field is always 0. So now we know that del cross B equal to 0. So we can write this velocity as a gradient of one scalar field. This scalar phi is called the velocity potential. Velocity potential. So, and this del phi can be written as dou phi by dou x I cap, dou phi by dou y j cap plus dou phi by dou z k cap. So if we compare it to velocity component, so u will be dou phi by dou x, v equal to dou phi by dou y, and w equal to dou phi by dou z. Now for the steady flow, if we see, then continuity will be del dot rho v equal to 0. It can be written as rho del dot v plus del rho dot v equal to 0. Del dot v is nothing but rho del square pi del rho is dou rho by dou x I cap plus dou rho by dou y j cap plus dou rho by dou z k cap dot v also we can write in the form of velocity potential dou phi by dou y j cap plus dou phi by dou z k cap equal to 0. So it can be written as dou phi xx plus phi yy plus phi zz. This z denotes the derivative. This subscript denotes the derivative. Like phi xx is dou phi by dou 2 phi by 2x square equal to dou by dou x phi x dou by dou y phi y plus dou by dou sorry plus phi z equal to 0. This we got the continuity. This is applicable for the compressible flow. This will be applicable for the steady compressible flow at rotation. Similarly, we also derive the momentum and energy equation, and we have taken extra assumption of isentropic flow also here. So this can also be derived, and using solving these all three equations together, we can solve for the compressible flow for heterodacial isentropic compressible flow. There's one more topic which was taught in the class, which was related to the shock tube. Shock tube have different sections. One section is driver, another is called driven. Driver is filled with generally light gas, and it is filled with heavy gas. And both are separated by one diaphragm. So whenever this, due to the high pressure of this driver, this diaphragm bursts, then what will happen is shock wave will travel in the driver, and expansion fan will travel in the shock wave will travel in the driven part, and expansion fan will travel in the driver part, and there will be one contact surface between both gases. So due to this moving shock, the pressure and temperature of air will increase, and due to this expansion wave, the pressure and temperature of this driver will decrease, and the change will be such that at the contact surface, pressure and velocity will be same. There will be difference of temperature, density, entropy, but these two conditions, pressure and velocity, will be same. When this shock will travel and hit the ball, it will reflect back. It will reflect back, and this expansion also will reflect. Due to this reflection, and there is wall, here velocity will become 0, and due to this moving shock, here pressure and temperature will once again increases. So this stagnation gas will be at very high pressure and temperature, and this is the concept of the reflected shock tube. And for the shock tunnel, this section can once again be connected to the nozzle through the tech section, and this gas can be expanded and used as the test gas. Generally, the test time which we get using this shock tube is maximum we get 1 millisecond to 2 millisecond maximum text time we get using this, and we use it to study the hypersonic flow. Uh, because it is not possible to conduct the flight test every time, so this ground-based facility is made to generate the flow property, free stream properties corresponding to the flight. This shock tube is only one of the facility. There are other facilities like expansion tunnel. In shock tube also there are different type of shock tube. This shock tube which I told was the conventional type. There is also arc type, combustion type, and detonation type. Similarly, there are facilities like expansion tunnel also. Which uses the unsteady expansion to increase the enthalpy. And all the facility which I mentioned are impulse facility. Impulse facility works for a very short duration, and it can generally we use impulse facility because in the flow, if you see in the re-entry flow, temperature can be go as high as 10,000 Kelvin also, but it is very challenging to make any tunnel which is structurally strong to strong strong for that temperature for a long time. So we use the impulse facility. So flow will be only till some microseconds, and it can withstand that temperature for this short duration. That facility can withstand that temperature for a short duration, and we get the useful data using the different sensors and flow visualization techniques like filtering, shadow graph, etc. So, is there any doubt? And does anyone have any doubt?
Sir,
Hmm?
sir, yeah, which section is high pressure gas section, sir? Driver or driven section?
Driver is high pressure section gas.
Yes, sir. Thank you, sir.
Driver is a high pressure section. Generally, these two are filled at different pressure. Generally, we use the light gas because if we use let's say you know the pressure here, you know the pressure in this section, you can find the relation between pressure ratio. Let's say this is 1 and this is 4. This numbering is then generally universally accepted numbering, you can say. Generally everywhere we use the same number. So this 1 will become 2, and this will be the 3, and this will be the 4. So using the shock relations, you can find the condition at 2 and condition at 3, and we also know the condition at this contact surface. So using all these relations, you can find one relation for P2 by P4 by P1, which will depend on the you can say shock speed, function of shock speed A1 and A4, and gamma and molecular mass of these gases both. So if we use the light gas here, then we can get the high shock Mach number, which will be useful for generating the which will make here stagnation gas will have high pressure and temperature. It will be useful for generating the flow. So generally light gas is used here. Any other doubt?
No, sir.
Okay, so today I talk about only fundamentals which will be useful in the course. So these are related to only compressible flow and thermodynamics mainly. So you can also refresh your memory and study with both this thermodynamics and compressible flow. It will be very useful in the further week lectures. And then from the next lecture it will be the proper start of the course, because it was introduction only for this week. So if someone has any doubt, they can also ask in the discussion forum of the course also. Then if anyone has any doubt, otherwise I will finish today's class. Okay, then bye, see you next time.